Thanks everyone for joining this session. Today I'm going to talk about mixture of recursion that we put it on archive a couple of weeks ago. It's basically a new types of, let's say, architecture to have different kind of access of efficiency in one place. Okay, this is a very, sorry, what happened? Okay, this is a collaboration between different places from Kai's AI, Mila, Google Cloud, Google Research, Google DeepMind, and these are all the peoples involved. And this, yeah, yeah. For some, okay. So I'm gonna start with the motivation. Sorry, I have one technical issue. I cannot see myself and everyone else in the chat. If you had any question, just pause because I cannot see the chat and the audience. So I'm going to talk about the motivation first. We wanted to come up with the architecture that has 3 axes of efficiency in one place, and previous works have tackled each of them individually, but we saw a lack of a unified architecture to be efficient during pre-training, and also in a way that we can leverage it at the inference. So I'm going to start with each of these, this one, and then I will go over some of the previous works first. So memory efficiency, we started with the parameter sharing. Parameter sharing has been used in the literature to make models smaller, and with sharing some layers or parameters, and so for example, when you have 9 billion parameter model, if you do parameter sharing, you would eventually be able to shrink it to 3 billion parameter model. So the memory efficiency comes from parameter sharing and has been explored in the original works, which is called Universal Transformer, but by Mustafa Dehkhan. And it was in the encoder-decoder architecture, we had this encoder which having a loop over it, which so we basically reusing the stack of shared layers across multiple loops. And again, with having the same kind of architecture in the decoder phase, then we have a multiple iterations over the stack of layers. And after this stuff, Simon, the other author, have explored this idea to make pre-trained model smaller by different types of parameter sharing strategies. So we can imagine you have 6-layer model, you wanted to make it smaller to shrink the parameters by half. You have different ways of choosing these parameters. And then again, you have a loop over these layers. And then there's another advanced version of it, which explicitly explored in this work. Simon used LoRa weights to compensate for these sharing strategies to maintain performance as much as possible. And also this looping strategy, which also can be considered as thinking in the continuous space. Let's say because you don't necessarily go through the token space, you have a loop over the representation, which is continuous. So we can imagine that you would be able to have this thinking step in the continuous space. So this axis gives us memory efficiency, and when we come to compute efficiency during pre-training, especially during pre-training. And people have explored these ideas through routing strategies. For example, one famous one is Mixture-of-Recursions paper by Google DeepMind, and they wanted to spend the compute more wisely based on the difficulty or importance of the tokens at every individual layer. So we have a layer, and then we have a router scores for every tokens, which basically tells us which token is kind of important or which token is more valuable to do computation. So we look at the the router scores and then pass it through the computation. If the score is low, that means that tokens should be bypassed for bypass the computation. So we save compute here based on the difficulty of the samples. And a similar idea has been explored in switch transformer, or more recently mixture of expert ideas, where basically we use the router strategy to define appropriate set of experts for every token. So we don't want to have a dense architecture. We want it to be sparse, so we have more efficient pre-training, and also we can leverage these types of efficiency during inference as well. Yeah. So this one basically gives us compute efficiency, and then we are going to look at the inference efficiency as well. So previous works have explored inference efficiency by stopping processing tokens when no work is needed. What do I mean by that? For example, in the layer skip paper, the authors are define a new types of inference approach to exit at intermediate layers when we assume the further computation is not necessary for those tokens. So here at inference, we save compute, so the throughput should be higher. So similarly, in the previous work by the authors in our paper as well, Tal and Adam, I guess, they explored this idea further and they defined column architecture. So here, where we wanted to combine all of these source of efficiency in one architecture, we want to use parameter sharing to save memory. We want to use early exiting to maximize the throughput. And also we want to use router strategy to spend the compute more effectively. So here we revisit the parameter sharing strategies in the paper. We have two main strategies. One is cycle and the other one is sequence. Cycles mean, let's say we have a stack of layers and then we have a loop over it, similar to previous work that I was mentioning. And the other one is sequence strategy. You can assume you have a micro loops over individual layers. And then instead of having a stack of layers, you have smaller layers and then having a loop over them. And we define different two variants of these strategies, which we call it middle strategies, where we fix input and output layers and sandwich these recursive ideas in between. And in a sense, we have, for example, for the middle cycle, we have input and output, and then we have again a huge loop over this stack of layers. And similarly for middle cycle. We explored these ideas, and a spoiler alert, we found that the middle cycle works the best, and our results are based on that, and I will later show our operation on these ones. And for the compute efficiency, you can imagine every next iteration in the looping strategy in the middle cycle, we have a loop over the stack of layers. Every recursion step is considered an expert for us. And we explored two types of routing mechanism. One is called mixed expert choice routing, which in the beginning of every recursion step, we look at the scores of the router for every tokens and select the top K tokens based on the scores. And then when we go to the next step, again we look at the router scores for all the remaining tokens. We do it progressively. So every token that has been dropped is not going to be used again for for computing the scores. So we again compute the scores for these ones and find the ones with highest scores, and then do one more recursion steps. So the name comes from this mixture of recursions, and then based on the router scores. And another approach is token choice routing, which we have a router which is basically a classifier and tells you which token should go through how many recursion steps, or let's say expert at the beginning. So there are pros and cons for these two types of routing mechanism. For example, expert choice, because it gives us a static compute budget. We select top K, so we are good. And the cons of it, because it violates the causality in the autoregressive manner, because we look at all the scores to select top K, but at the inference, we want to predict one token. We don't have any other tokens to compare the score of that one with. So we, similar to a mixture of depth paper, we explore having an auxiliary router, which is going to mimic the behavior of the main router for just one token to use it at inference. When we wanted to predict the next token, that router tells us how many recursions that we should spend. And yeah, another approach to solve this issue, the causality issue, is to having auxiliary loss, one binary cross entropy loss over for the router to mimic the behavior of the auxiliary router at the same time. And again, a spoiler alert, expert choice routing plus auxiliary loss works the best, and it's very straightforward. But on the other hand, we have token choice routing, which doesn't have the leakage problem, because it looks at any token and gives the associated number of recursion steps. But there is a problem which is now in the literature, which is load balancing, especially in the mixture of expert papers. There are different ways, for example, from DeepSeek and other papers that we explored. But comparing to expert choice routing, it was not performing very well. Any questions so far? No? Can someone say something? Like
I got a quick question for you.
Yeah, good.
If it's loss free, how does it actually learn?
Basically, we wanted to bias the router by a statistic. We look at how many times one particular router has been used. We keep track of it, and then specifically consider that in the assignment. Yeah.
Oh, interesting. So like a proxy that it can use for learning.
Yeah. I mean,
That's cool.
I guess DeepSeek is using a loss-free approach for the expert for mixture of recursion, mixture of expert architecture. Yeah.
So Reza, so far people are still absorbing your talk, so we're gonna let them listen further and put the questions in the chat.
Awesome. Okay. And another advantage of having these recursion steps is, as I said, we can do early exiting. We can do early exiting based on the router score. So when some sequences exit, so that means we have free memory. So how can we basically maximize our GPU memory efficiency? The way it's been explored, it's especially, I guess, been used in the relaxed recursive transformer by Sangmin. We have something called the continuous stepwise batching. And let's say we look at the most right plot. The maximum number of sequences that you can fit in a memory is 32. So the batch size is 32, and you have an input stream. And the input stream, at each stage of the model, you will process some of the sequences in the batch. And when you go to the next stage and when you receive the next input stream, you can feed those uh, uh, extra sequences to maximize your GPU memory. But again, because we have this exiting strategy, some of the tokens can exit early, and then we free memory, and then we can feed in more input from the stream. So the continuous steps of batching comes from this mechanism. We have a stream of input, and then we do the computation, and some of them are exiting early, so we can feed more sequences from the stream. That's it. Yeah, and I guess there are a lot to observe, but the most interesting part of it is having KV caching and sharing mechanism, which comes from this by design. And recursive wise KV caching means at each recursion step, we only select, we only keep the KV caches of the selected tokens. Because we are progressively pruning the tokens, we won't need the remaining KV caches, and then we save the precious memory during inference as well by just keeping the KV caches of the selected tokens. And there is another way that is very suited for recursive paradigm is to reusing the KV caches from the earlier recursions. So because we feed all the tokens through the first recursion steps, we have all the KV caches for all tokens, and for later recursion steps, we can reuse them. But again, spoiler alert, recursive-wise KV caching works very well, but this one, recursive KV sharing, has some performance drop, but not significant. But it's very efficient. You lower the number of KV caches, and also the KV cache IO is much lower. And putting everything together, we comes up with this architecture. We have router to select the important tokens to do the computation, and we have a mixture of these recursion steps based on each tokens, and then we have early exiting inference. So if you wanted to take a look just to one example, here is the middle cycle strategy. We have the input layer and the output layer, which are fixed, and we use them for every tokens. And the middle ones are the recursion steps. This is the first recursion step, second recursion, and so on and so forth. And this one, the first token has gone through all the layers, all the recursion steps, 3 recursion steps, but this bunch of tokens only been used for 1 recursion step. So all of these skipped computation step are our memory efficiency, compute efficiency at the same time, because we only keeping the KV cache of these selected tokens, and because the context window is smaller, the attention mechanism is much cheaper for this stuff. Yeah. I'm gonna go over the results now. Yeah. But maybe if someone has a question,
I think people are still absorbing.
Yeah.
Go ahead.
Yeah. Okay. So here is the main result. Under the same compute and token budget, our MR approach outperforms the vanilla transformer. The first row is the vanilla transformer with much larger number of unique parameters, and this is the recursive baseline, and this is our MR approach. Under the same compute budget, here, we can increase the number of tokens being consumed during pre-training. Then as you can see, for this number of recursion step 2 and 3, we outperform the vanilla model. And more interestingly, under the same token budget, by varying the amount of compute, we still, with the 2 number of recursion step, we still outperform the vanilla. So we are thinking these dynamic dropping tokens make the task prune the unnecessary token, unvaluable tokens, and then the next token prediction task would be easier or more effective. So instead of just saving compute and other stuff, these dynamic dropping tokens had some advantage during pre-training as well, just from the objective perspective.
Hey, Reza, can you remind folks of the basic experimental setup, what base model you used and so forth?
This one, we use a small LM model with which was the total number of parameters is 360 million, but the total non-embedding parameters are 350 million. But as we for the vanilla model, but because we have recursion steps, as I said, we are saving memory there. We are making the model smaller. So through the recursion step, we are dividing the number of parameters by 2, and so on and so forth. Not exactly by 2 because we have the fixed input and output layer, but roughly the number of parameters are divided by 2 and 3. So we have a much smaller model. And then because, yeah, the model is smaller, but
The point
when you
is
unroll it, it seems like you have, sorry, go ahead.
you did pre-training from scratch, right?
Yeah,
Because it's a brand new architecture. You need to do from
yeah,
scratch.
yeah, everything's, yeah.
What data set did you use? The pile?
It's 5web edu deduplication version.
Yeah.
Yeah.
Cool. So yeah, just
And
to
these
remind you,
are,
this is one of those rare, truly made from scratch model situations. Wanted to make sure everyone knew that.
yeah, yeah.
You don't see that every
Thanks
day.
for, yeah, and thanks for mentioning it. Yeah, everything from scratch on 5web edu deduplication version up to, for this one, up to 30 billion, but we also tested on more in the scaling studies. So for every new architecture, it is natural to ask if it scales or not. So in the main experiment, we use this size of a model, which is 360 million base model. And we use a smaller and also bigger model. When we go very small model, which is 135 million base size, which means in this setup we use 3 recursion instead, which means our MR model has 45 million parameters. We see MR outperforms a standard recursive model, but doesn't outperform the vanilla model. We are assuming this routing mechanism and dynamic compute allocation would be difficult at a small scale. But as we scale the model, we see the advantage of this paradigm, this new paradigm. And especially you see we roughly outperform or match the performance of vanilla under higher compute budget. We definitely outperform on the middle compute budget, all of the models. Yeah. So this plot basically tells you that you would potentially be able to use MR at larger scale. For example, DeepSeek has around 700 billion parameters. So with these new types of architecture, you can lower the number of parameters by 3, and which helps you to serve the GPU, serve the model on less GPU. Yeah, this GPU memory. And I guess the last main thing that we wanted to discuss, which is the most interesting part, is maximizing the throughput. because we have early exiting and the continuous batching and also KV cache sharing, recursive wise KV cache sharing, we can serve more sequences with this paradigm. Comparing to vanilla, everything has been compared to the base model, the base vanilla model. Please look at the orange color. This is where we call it the max, which max batch size, which means because we lower the number of parameters and everything else, we can increase the batch size for MOR compared to vanilla model. And as you can see, with roughly tiny performance drop, we could increase the throughput by factor of 2, which is significant because it seems like pre-training is not the bottleneck at the moment. We wanted to deploy models everywhere, so having faster model would be a huge advantage. So MR gives you two times faster throughput, basically, with almost no performance drop. Yeah. So in one sentence, we design an architecture which helps you to have a smaller model with higher accuracy and greater throughput. So everything in one place, basically. And yeah, so far what I discussed was the main results. If there are no questions, I will go over some analysis. Yeah.
Oh, we have a question.
Cool.
Excellent.
Can you read it for me? Thanks.
We can actually, yeah, Raj, would you like to read it or bring him up to the stage?
I just invited them to unmute.
The microphone.
I cannot hear you very well.
It's okay. We can just read the question. So the question is, do the number of recursions applied to each individual token change when you keep generating more tokens? How much does distribution evolve over time?
When we are generating, the router defines if one particular token should go through more recursion step or not. If the score is lower than the threshold, it's gonna be exited, and if it is higher than threshold, it's gonna pass through more recursion steps, and then we will predict it.
I think the question is like, what's that distribution look like?
Distribution of the router?
Recursions per token. Is it like a power law distribution?
Oh, recursion. Oh, okay. Distribution of the so during pre-training we explicitly have this pruning ratio. For example, the first recursion step consume all the tokens. For the next recursion step, we drop 33% of the tokens, and for the recursion afterward, we drop another 33% tokens. So we progressively prune the number.
How did you settle on those magic numbers? Just practical?
Yeah, we actually didn't do many ablation on it, but because it's very computationally expensive to have a broad ablation on it. But we can imagine that there could be more effective ways to do it.
Oh, interesting. We got another question for Raj from Richard. Can you bring him up?
Yeah, thanks. So yeah, really cool talk. So I have a quick question about the parameter sharing part. So you mentioned that the middle cycle works best, right? So they have the unique first and last layers, but the middle part is the one that is shared, right? So I just wonder, what's the intuition behind this? Do you think that because the first layer and the last step, the input and output, they are like special, while the middle part is like the thinking part is more like repetitive and this can be shared? Like, what's the intuition behind this?
That's a very good question. To be honest, I don't have a clear explanation for that. For the last block, I guess having one extra look at one extra look over all the tokens might help the next token prediction task. But maybe I can ask other authors if they have any comments on it. Simon and Eugene, if you feel free to
Yep.
make any comment.
Yeah, I can go over the questions. So I feel like this one is like consistent with some intuitions from people who are working on architectures. So it's like people are thinking that like first and last layers are critical to get the correct predictions. Like so when we do some depth scaling for the like language models, so when we want to scaling up the depths from 20 pre-trained checkpoints to like 40 things, what they usually do is like they just use the fixed first like 3 layers parts and the last 3 layer parts, and then they just like repeat the middle ones like this. And I feel like yeah, it's just aligned with the like just conventions from the architectures, but we don't have any like proof, like clear proof, like because it's really hard to compare between cycle and middle cycle in a fair comparison, like the same parameter, exact same parameter sizes or something. So yeah, we just follow that intuitions to get this result. Yeah. Thank you.
Thank you so much for your comment. Thank you.
Thank you.
Looks like there's one more question, Reza. So the question is, in the results table, it seems that there's not a clear relationship between more cycles, e.g. 2 versus 4, and it seems more cycles is actually worse. Do you have any idea why? Did you see the same pattern on other benchmarks?
Yeah, I guess that's a good question, but it comes from a misunderstanding, because number of recursions doesn't tell you are spending more compute in the sense that unique compute, because when we go for more recursions, we are making the model smaller. So it doesn't look like that we have a fixed number of layer and do more recursion over them. When we do 3 recursions, the number of effective unique parameters are smaller, so that the capacity of the model is going to be limited. So it makes sense the performance drop. But we also have we don't have it right now, but we have an ablation that we took the same size model, for example, 165 million model, and did recursions for the 2 or 3 recursion for those, and we actually saw that if you do more recursion and stuff on the same base size model, you would get the better performance. I hope I answered that. Was it clear, or I should explain more? I mean, the main point is with 3 recursions, the model is the unique number of parameters are smaller, so the capacity of the model is limited. Yeah.
They said it was clear. Thank you, Reza.
No worries. Okay, I will go over some analysis. This is our ablation on different types of cycling parameter sharing strategies. And as I mentioned, the middle cycle, the green one, is outperforming other types of sharing mechanisms. So we picked this one for our rest of experiment. And again, for the router choice experiment, we have done ablations based on different types of architecture for the router, MLP router, linear router, and wide MLP, and different activation functions, and also different sampling strategy, having an auxiliary router or having auxiliary loss, as I mentioned, for the expert choice. And similarly for the token choice, we have gone through different architecture, activation functions, and different ways to solve this load imbalancing issue. But eventually we found that having expert choice router with auxiliary loss has lower the tokens, I would say, or it's more balanced compared to token choice routing. So we picked expert choice with auxiliary loss instead of having auxiliary router. And this is also interesting observation based on why we can do KV cache sharing from one recursion to another recursion, because these experiments are with the 3 recursion steps, and each layer is, when we unroll it, is associated to the beginning, to the next block, next layer in the next recursion step. And as you can see, between every KV cache vectors, there is a high cosine similarity from one recursion to another recursion. So it makes sense to use earlier KV caches for future computation. And the last thing is some samples of how these mixture of recursions look like. You would see that there is a mix of computation based on the difficulty of the samples, the difficulty of the tokens, or some other statistics. But so just wanted to show this last part, that there is actually a mixture of this stuff.
Reza, in that plot,
happening.
is blue low recursion?
This one, blue is 1 recursion, purple is 2 recursions,
Okay, cool. That makes
and
sense.
the other one is 3 recursion.
Yeah. Cool.
That's all. Thank you so much. Any questions, I would be happy to